So now we're going to start looking at sort of like a different aspect of some of the math part, like underlying math part of what we do in terms of physics and that type of stuff. And we're going to look a little bit at, let's say we're going to look at sort of like patterns and formulas. Sort of like really like where formulas come from, how do they actually make formulas and that type of stuff. Now we're just going to start basic, just show you the general idea. Suppose, let's take this. Let's suppose I have like a series of numbers. Okay, so suppose I've got like, we can just use like A and B. It doesn't make any difference. But suppose, we have some values for A that look like, we'll do something really simple, like 1, 2, 3, 4, and they just keep on going. And we got some B values. And the B values, let's go like 3, 6, 9, 12, and keep on going. And I asked you guys, what is the connection between A and B? So what's the connection between those two values? Now, I mean, this is really simple, really straightforward. Now, when you say what's the connection between them, or what's the relationship, what's the relation between them is often a nicer way to look at it. One thing that you might pop into is saying, what's the relation? What's the connection? Oh, that's easy. B is equal to 3 times A. Well, that's not exactly what I'm asking you for. What I'm asking you for is what's the connection? What's the relation between them? How does one change compared to the other? I'm not asking for the formula. I'm asking for the relationship between them. The same way if I gave you a different set of numbers, maybe I gave you, C and D values, and the C values were 1, 2, 3, 4, and my D values were 3.1, 5.8, 9.3, and 11.7. And I asked you the exact same question. What is the connection? What is the relationship between C and D? And then just saying that D is equal to 3 times C would fail, because not one time does that work. So it's not really necessarily about how to calculate one for the other. It's about how do the numbers change. That's sort of what you're looking at, is how do the values change, or maybe compare is more specific. So if we looked at the A and the B values, if the A values 1 to 4, 3 to 6, they're always changing by the same amount. They're always going up by 1 for the A's, they're always going up by 3 for the B's. They're always going up and changing by the same amount each time. And because of this, I know that if I would graph them, that's what you guys have often done. If you would graph them, it would look like a straight line. And that tells me the connection or the relationship between them. These two values, the A and B, the relationship is linear, or you might say directly proportional is the relationship between them, which tells me as one goes up by the same amount, the other one is going to go up by the same amount. So they are directly proportional to each other. And more specifically, B would be directly proportional to A. And you can think of like Y proportional to X type thing as well. But I mean, it's B is directly proportional to A. This exact same thing applies to C and D. And it's not really about calculating one from the other. It's how the values are changing. If I look at, the C values, it goes up by 1, it goes up by 1, it goes up by 1. That's nice and easy. And if I look at my D values, they're not going up by the same amount each time, but these guys are going up by about 3-ish each time. And if I look at the gaps, you can subtract the two and look at the differences. It's about the same amount each time. We have very, very similar gaps between the values. They're all around 3-ish. They're hovering around 3. So it's not about how much they're changing. It's like the trend that you're looking for. And these two, C and D, just like the one above it, these two would make a graph that looks generally linear. And just like the other one, they are probably directly proportional. And I'm saying probably because you don't necessarily know for sure, especially if this is experimental data. It's not guaranteed until, I mean, we've only got 4 sets of numbers. There's almost nothing here. But we're looking at similar gaps, which means they're probably directly proportional based on what we have, and D would be directly proportional to C, and that's the idea that we're looking for. If we make C twice as big, D will also probably get twice as big. That's the idea that we're looking for. How do things change? How do they compare? Okay, let's take something else. Suppose I've got... let's go with E and let's go with F. And let's do it nice and simple with E, you know, like 1, 2, 3, 4, blah, blah, blah. We have some F values. And our F values, let's say, are 5. Let's go with, we'll make this too hard. 14. Let's go with, oops, let's erase that one. That's not what I wanted there. I want, oops, wrong tool. I want 29 right there. And then for our last one here, I am going to put 45. Okay, and I want the connection between the two. Well, first things first, it's not about the values I have, it's about how they're changing. So if I go here, you know, this is going up by 1, that's going up by 1, that's going up by 1. That's just super easy. If I go to the bottom set, here I went up by 9. Here I went up by 15. So right there, that's not a similar gap. Like that's a pretty big gap. And here I went up by 16. Well, that is a similar gap, actually. That's kind of interesting. So it's, you know, and this is a very limited set of numbers, but it is possible that it's still linear. This gap right here is a little bit low, but maybe it's just that one. So those two values, again, they could be directly proportional to each other. Having more data would definitely kick in. You could see if maybe, you know, the 9 is way off. If, you know, you got a 15, you got a 16, then your next gap was 15, then 14, then 16, then 17, then 15, and your gaps were similar, then the 9 was probably a little bit weird. But if we kept on going and, you know, the gap was 9, then it was 15, then 16, the next gap was 20, the next gap was in 35, and the next gap was in like 50, well, then it's not going to be linear. So sometimes it can be really, really, really hard to tell with a limited data set. So let's change this up a little bit. Let's give some more values here. We'll get rid of this right here. Maybe, you know, our next number here was 5. Okay, so no big deal. So make that 5 right there. And then our next number here is going to be 72. And then it keeps on going. Okay, so a little more information. Okay, this gap is 1 again, no big deal. But the gap between 45 and 72, that's a pretty big gap. We're looking at a gap of like, oops, not 37, 27. Let's erase that. Carry that over there. Okay, so we got a gap of around 27 right there. Okay, so now looking like this, you know, the top values are going up by a nice constant amount. The bottom part, you know, these two are similar, but all of a sudden skyrockets again. This does not look linear. If I was going to sketch a graph of like this, it would probably look like it's going to curve, which means they're probably exponentially connected, right? So it's not a directly proportional relationship. It's probably an exponential relationship between the two. Again, more data, make it better, but based on what I got, it's probably looking like it's exponential. So I don't know for sure, but F is probably connected to E squared, not just E. Again, it's just an estimate, get an idea what's going on. That's all I'm really looking for. Okay, if you had exact values, that's different. But I'm just trying to see how one value can connect to another value. All right, and that's generally what we're looking for. Again, not knowing the situation, having a very small data set, blah, 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 it can be hard to know exactly for sure, but that's not the point. The point is to have a general idea, so like an estimating thing, estimating the relationship between different things. Okay, now the thing is for the top one here, this one is easy. I mean, the B is equal to 3A. That you can get the formula for. The green one here, if it is a similar relationship, it's probably D is equal to 3C. You know, it's probably the basic expression. For the last one here, it's probably F is something with E squared or something like that. That's generally what we can lead to. But it's all, again, general idea of how one value will compare to another value. How will one value change something else? Okay, and you can even go to an expression to sort of see this thing as well. This is more like a data type thing. But what if we have expressions instead? So let's get rid of this. Let's clean this up right here. All right, so what if instead we had an expression, okay? And this is more like connect like your math type stuff that you guys are working on. Like, and we'll even do like here, y is equal to 3x squared over z. Okay, so with this little expression here, which variable is the most important? Which one has the biggest effect? Well, hopefully you're jumping to the x, because of that squared will have a much larger effect on the value than just the z, because you're just dividing by z. Where on the other hand, if we modify the expression and said like y is equal to 3x squared over z to the power of 4, now this one right here, that power of 4, now the z would be by far the most important variable, have the biggest effect on the y value. So sometimes what we want to know is which variable, whatever you want to call it, has the largest effect on the situation. You want to know, like, will it make it twice as big, half as big? Which is going to be the biggest effect? Okay. So, for example, let's take an expression that you guys have actually looked at before in actually grade 11. I showed you this expression for force of drag, so 0.5 CD rho A V squared. This is an expression that I showed you, introduced you in grade 11. We didn't really use it for much of anything, but I showed it to you. And this is to calculate, of course, the drag force on something. Now, you got the 0.5, you got the coefficient of drag, coefficient of drag, you've got the density, the area, and you got the speed. And between these 1, 2, 3, 4 letters in here, or symbols, which of those 4 has the biggest effect on the drag? Well, it's the V has got the biggest effect because it's got that squared on there. If you make the coefficient of drag twice as big, drag is twice as big. Same with the density, same with the area. Those will all just double. But if you double your speed, your drag will become 4 times larger. And that's the type of idea we want to look at, is which variable has the largest effect. So often when you're doing this, you want to often look for exponents, because often the one with the biggest exponent is going to have the biggest effect. Okay, and that type of thing. Now, another really kind of cool thing that kicks into this type of situation is how to actually make formulas in the first place. Now, in order to do that, there's different things that got to kick in. You got to see how variables connect, what connection they actually have, that type of stuff, and we can sort of piece things together. Now, I'm going to show you a little something here to sort of show you how this type of thing actually works. So here I've got a formula. I've got 6s cubed will give you r. Okay, so I've got r is equal to 6x cubed. Now, what I've got in my little table of values, I've got r values, I've got s is equal to 1, 2, 3, 4, 5, s squared, s cubed, we'll worry about that later on. Now, on the right, we've got a basic r versus s graph. And if the s values go up by 1, 2, 3, 4, 5, blah, 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 I mean, you guys done lots of math before. R equals 6x cubed is going to be an exponential graph. You know it's going to curve. You know it's going to look something like that. Okay, that's no big surprise. But the problem with this graph is I want to find out where the 6 comes from. Like, where does that 6 kick into this situation? Like, why is there a 6 there in the first place? Now, it's a constant. The 6 doesn't change. So where do these constants come from, these constant random values you see in front of formulas? Well, constants come from slopes of graphs. But you know this curve right here has got lots of slopes. I mean, you guys have done tangent stuff before. So that doesn't work really well. If I want a constant, I need to have a straight line. So to do that, what if instead of graphing r versus s, what happens if I graph r versus s squared? So I take my 1, 2, 3, 4, 5, and I square the values, and I graph those instead. Well, if I graph those instead, what can actually happen is the graph will change shape. So if I graph it again after I do that, this is r versus s squared, the graph looks something like this. And hopefully you can see this graph is actually straighter than that graph. All right. So a couple things have changed. You know, the values have changed on the sides here, or on the bottom here. The spacing's changed a little bit, but actually has straightened out compared to this one. But what if I would graph r versus s cubed instead? So now I'm going to cube the s values. And if I graph that one, it actually turns to a perfectly straight line. Now this throws people off a little bit because they're going, hey, wait a minute, it's s cubed. When there's an exponent, it's a curve. No. That's a little bit different. I'm not graphing r versus s, which did give me the curve. I'm graphing r versus s cubed, which actually creates a straight line, which means I can calculate the slope of that line. And guess what that slope of the line is going to be? The slope of that line is going to be 6, and that's where the 6 comes from. So why it's straightened out, there's reason behind it, but it's all about when the exponent is actually being applied to the expression. Here, if we go back to the first one to get the curve, you take the s value, you double the s value, you then apply an exponent of 3 to that difference, and then the r value skyrockets. When we get to the bottom part here, we're not changing the s cubed value and then cubing it again. That's already been done. Once I've doubled the s cubed value, that's it, and that's why it creates a straight line. So again, it's a little mathematically, it's a little bit counterintuitive to what you guys are used to seeing, but this is generally how it works. So, and once you get the idea, it's actually really simple. Okay, let me show you another one. Okay, let me show you this one. Here we got r is equal to 6 over s squared. Now, again, if you got r is equal to 6 over s squared, it's an inverse. It's going to curve down, look like something like that. Well, what if I don't do a graph of r versus s, and that's an r versus s graph. What if instead I graphed r versus 1 over s? Now, of course, you see the 1 over s, the first thing that pops into your head is an inverse graph, like what's shown there. But no. R versus s gave me a curve going down. If I do r versus 1 over s, it actually flips the graph to go up. And if I then go back to my expression, r is equal to 6 over s squared. If I do r versus 1 over s squared, it actually turns into a straight line. It straightens out the graph for me. And the slope of that graph would be 6, and that's why there's a 6 in front. Okay, so again, some of these shapes might be a little bit counterintuitive to what you're used to, but that's sort of how this works. Okay, so let me get rid of this. All right. So let's sort of show you how this type of thing works a little bit. So let's just start with an expression and sort of lay things out. Okay, so we'll put a little divider right there. Okay, so when you actually make formulas, what you do is you want linear graphs is what you want, and you want them in order to actually get constants. Okay, that's what you want. So, for example, let's take something really simple. Let's actually use this expression right there. If I would do, the 0.5 is nothing, no big deal. If I did a force of drag and coefficient of drag graph, and I plotted a graph, it would give me a straight line. There's no exponent here at all. It would give me a straight line. Okay. If I did a force of drag, not coefficient drag, a row graph, the density graph, it would give me a straight line. No problem. If I did a force of drag, run out of room here, area graph, it would also give me a straight line. But if I did a force of drag times v, it would give me a curve, right? There's a little 2 on there. Force of drag, coefficient drag, no problem. The force of these two are directly proportional to each other, no problem. Force of drag is also directly proportional to rho, no problem. Force of drag is directly proportional to the cross-sectional area, no problem. the force of drag is not directly proportional to the v, and that's why I get a curve out of it. But if I change this graph, instead of graphing force of drag times or to v, if I graph force drag v squared, it would actually create a straight line, which tells me the force of drag is directly proportional to v squared. And that's how I know how this formula pieces together. And that's sort of how it comes out of play, and that's how they make them. Now, the thing is, I've got 4 linear graphs. I've got this one, I've got 2, 3, and 4. Each one of those graphs has a slope. There's 4 slopes. Okay, I'll call this, slope 1, and I got slope 2, and I've got slope 3, and I've got slope 4. If I would take those 4 slopes, m1 times m2 times m3 times m4, if I would take those 4 slopes together, they would give me 0.5, and that's why there's a 0.5 in front. It's not just a random. Sometimes you see formulas, you see that type of thing, and there's this random number in front. It's not a random number in the front. It is actually the slope or combinations of slopes of all the linear graphs that were used in order to make the formula. Okay, and that's where they come from. That's where all these constants come from. Okay, take the most simple one there is. Okay, take a graph for a circle. If you do the circumference graphed by the diameter of a circle, you will get a straight line. And the slope of that line, of course, is pi. And that's why circumference is equal to pi times d. It's this exact same idea. But when you have more variables, you combine the slopes together. Okay, and that's why that 0.5 is sitting in front. You think some random piece of math garbage. No, it's there for a reason. Okay, so let's clean this up a little bit and tone it down and show you some more examples of how this actually works. Okay, so let's get rid of this. All right, so let's take something, let's make up something here. Let's say we've got a is equal to 7 times b squared d over c cubed. Okay. And I want to see where this, let's see where this comes from, that type of stuff. So first of all, graphs. Okay, let's sketch the graphs of what these look. Let's start with that. So if I would sketch the graphs for this, if there's 3 main graphs I can make A versus B, I can make A versus D, and I can do A versus C. Now, if I would graph them, and all I need is like a sketch, get an idea what's going on. If I graph A versus B, B is got a squared, it's going to curve up. No problem. That's good. A versus D, there's no exponents, nothing weird going on. That's going to be a straight line. A versus C, you're dividing by the inverse or cubed, it's going to curve crazy like this. Out of the 3 graphs, the only one good to go is the middle one. I know that A is directly proportional to D, so that's good to go. The other ones are not good to go. A versus B isn't going to work. But if I would graph A versus B squared, I take the entire nature of it and graph that, it would give me a straight line. So that would tell me that A is directly proportional to B squared. Same thing for this. A versus C doesn't work. Okay, it doesn't work at all. But if I would graph A versus 1 over C cubed, the entire nature of it, it's C cubed is an inverse, the entire nature, it would give me a straight line, which tells me that A is directly proportional to 1 over C cubed. Okay, so then I could take these 3 things, and I'm going to piece them together. So if I would take these 3 and piece them together, A would be directly proportional to B squared D divided by C cubed. And that tells me how the variables all connect to each other. Now notice I didn't put an equal sign. I put directly proportional. I can't put an equal sign because I don't have the constant in front. So to get that constant, what I would do is I would find, slope for this guy, slope number 1. I'd find the slope from this one, slope number 2. I'd find the slope of this one, slope number 3. I would take those 3 slopes, and if I would then multiply those 3 slopes together, the product of those 3 slopes would be 7, and that's why there's a 7 in the front. And once I have the constant, then I could do this. I could say a is equal to 7b squared d over c cubed, and that's how it works. And this is what is done to make all formulas. Every formula you've ever used in physics, chem. Okay, so, I mean, we're here. Proportionality statements. These are the proportionality statements right there. And this is what you're trying to get, is these proportionality statements. And once they have that, they can make the formulas. And again, like all the constants you've ever used, that's where they come from. It's a combination of slopes. And if it's just one variable, it's just the one slope and that's it, no big deal. But if it's not, then you gotta have a combination of slopes put together. So the drag formula that you've had in chemistry, you got expressions, the random coefficients in the front. This is where they actually come from. So the whole thing is, they try and straighten the graphs, use the straightened graphs to actually make proportionality statements like a is directly proportional to b squared, a is directly proportional to d, a is directly proportional to 1 over c cubed, find the slopes, straighten them out. And literally, like for the C one, what they would do is, next they would graph 1 over C. Not straight yet? Okay, so let's try 1 over C squared. Still not straight? Oh, let's try 1 over C cubed. And they just keep on building and building and building until it's super straight. Now, the thing is, to do this, of course, they're using experimental data. They're not using perfect numbers like you guys are used to in math class. They're using experimental data. So they have to look at general trends, general patterns, and that type of stuff. And that's where the stuff really, really kicks in nicely. Okay, so let's get rid of all this and let's look at a different viewpoint. Sort of see how these things piece together. So maybe you got some data, you're graphing things out, and let's say you made a graph of x versus a, and it gave you something that looked like this. Then you graphed x versus b, and it looks something like this. And then you graphed a or x versus c, and it looks something like this. And you're wondering, hey, what's the formula for x with these 3 things? Well, first things first, none of these graphs are straight, so we'd have to try and straighten them out. So this first one here, it's obviously an inverse. So you try graphing an inverse. So you graph 1 over a instead. And as soon as you do that, it does this. Still curving a little bit, but at least it's going up. It's like, hey, it's still curving though. Maybe it's exponential. So you try changing it again. Maybe you graph x versus 1 over a squared, and then it looks pretty straight. Well, again, if you don't have any numbers or anything like that, you're just getting an idea of what's going on. There's a good chance that x is going to be directly proportional to 1 over a squared. Okay, then you go to the next one, and you got a nice little curve. So you try graphing b squared, and when you graph b squared, you end up getting a pretty straight line. Okay, no problem. So x is probably directionally proportional to b squared. You go to the last one, and you try graphing x versus c squared, and still curves. So, okay, well, let's try doing something else. Let's try x versus c cubed, and you get a pretty straight line. Well, then x is probably directly proportional to c cubed. So if you want to then put this all together, you can combine these all together into one expression. And if we do that, using this one, and this one, x is probably proportional to b squared c cubed over a squared. Now, am I perfectly correct? I don't necessarily know without having more data, knowing the situation. It's about having an idea of what is going on. Now, again, there's no equal sign. I don't have a formula yet. I would need to know the slopes. So let's just make something up here. Maybe the slope for this one was 2. Maybe the slope for this one was 3. Maybe the slope for this one was 0.25. I would take those slopes and put them together. I would do 2 times 3 times 0.25. And if you multiply those 3 values together, you will get 1.5, right? 2 times 3 is 6. Quarter of that is 1.5. That would then go here. And it would be x is equal to 1.5 b squared c cubed over a squared. And that would be the formula for x using b, c, and a. And this is how they can build formulas. This is how proportionality statements work, how to straighten the graphs out, that type of thing. That's how this stuff all comes together. Okay, so every formula you've ever used in math, physics, chem, anywhere, it makes no difference. This is generally how they are made. Find out what variables are important, how they connect to each other, try and straighten out the graphs, find the slopes, combine the slopes to make the formulas.